sort into R1 is getting replaced with R2. So you are row interchanging R1 and R2. So in the identity matrix, you know that, right? That A is equal to I into A. So if you do any type of row operations here, it is quite similar to doing row operations here, right? That what you might have done in your 12th standard only, when you were solving these type of augmented matrix to find the inverse. So what I'm saying is, you have this something of this sort: 0, 2, 3, 1, 1, minus 1, 0, minus 1, 1. It is nothing but equal to identity times this same matrix here. And if I now apply R1 going to R2, this implies, okay, it will be 1, 1, minus 1, 0, 2, 3, 0, 1, minus 1, 1 is equal to 0, 1, 0, 1, 0, 0, 0, 0, 1 times A, right? And now you can solve this matrix at least. You can find the LU decomposition of this matrix. Say it is B. Can you find the LU decomposition of matrix B?
Yes, sir.
So now what you have, if I make this matrix as P, then you have P into A is equal to L into U, right?
Yes, sir.
So permutation matrix has one more extra property. It is P transpose into P is identity, where P is the permutation matrix. So what you need to do, multiply both side by, pre-multiply both side in equation 1 by P transpose. Then you have P transpose PA is equal to P transpose LU. That is, A is equal to P transpose LU. Is problem number 7 clear?
Yes, sir.
Okay. Have you tried doing problem number 8? Are you guys having a look at these questions in the tutorial itself, or you are doing it at your home also?
We are doing also, sir.
So was question number 8 doable?
Sir, it is question 6 or 7 on the slide.
Which slide?
So what you have done is question number 6.
Okay, probably I have some other sheet. Okay, what is your problem number 7 in your sheet then?
Show that Gaussian elimination can be performed on A without row interchanges if and only if all leading principal.
Okay, so probably in your sheet you will be having around 8 question only, right?
No sir, 10.
Okay, but 8th problem might be Chomsky factor, right? Because she might have shared a different sheet with me.
No sir, 8 question is Gauss-Jordan method requires number of multiplications and addition subtraction.
But we have already discussed it. Okay, can anyone share the sheet with me in the chat box maybe? Do anyone of you sharing it? Okay, yes, it is shared. Let me see. Okay, let us perform. Okay, let us discuss question number 6, 7 then. So, was it doable? Is the question make sense to you? Gaussian elimination.
Yes, sir.
So, can we skip it? Or do anyone of you want a discussion on it? It is just an observation that if all the principles of some matrices, leading principle of the sum matrices is non-zero, then you can anyway do these 1 upon a11 stuff, right? 1 upon a11 or 1 upon a22 while doing Gaussian elimination, or one more thing which we have discussed in the last class, or maybe Gauss-Jordan method also. So if all the principle of the all the leading principle of the non-single of the sum matrices are non-singular or non-zero, then you can do this, right? But the question is asking you if A is equal to say Aij initially, okay, and then if A111 is non-zero, A22 is not equal to 0, and so on, ANNN is non-zero, then you can apply Gaussian elimination without interchanging any two rows, right? So it is just an observation if you see what we are doing there. Because what do we need to do in order to apply Gaussian elimination? We need to have these things with us and so on, right? Does this make sense?
Yes, sir.
Okay, come to question number 8. So we have done a similar sort of stuff in question number 4, right? Like how many multiplication and division operations we need in order to transform a matrix using Gauss Jordan or Gauss elimination. So have you tried doing this?
Yes, sir.
So was it doable or you faced any difficulty?
Doable, sir.
So can you show the proof to anyone else? Like, can you share the picture, or you guys can discuss it among yourself in the group? See, if anyone wants a discussion on that, I can do this. But we have already discussed something, a question of similar sort in the previous lecture. Okay, I assume that you can do that. Come to question number 9. Are you aware about do little method?
Yes, sir.
Yes, sir.
Yes, sir.
So have you solved this? It is nothing but the LU decomposition which have been taught to you, right?
Yes, sir.
Yes, sir.
So can it be doable? Or was it doable, or we need a discussion?
Doable, sir.
Okay, tell me what is your matrix L then? If you have solved it, what was your matrix L?
सर अभी मेरे पास सॉल्यूशन नहीं है इसका.
Okay. Okay, let us discuss question number 10 then. But everyone agrees that it is quite a simple problem to do.
Yes, sir.
Yes, sir.
Come to question number 10. So are you aware about the Chomsky factor?
Yes, sir.
Okay, so have you solved this?
Yes, sir.
So tell me what was your L? What L did you found out?
So 100
Right,
220
right,
333.
right. So A is the L into L transpose, right? So this L is our key factor. But the question is asking you one more thing. Have you solved that also? The question is asking you to write A is equal to some new matrix L into a diagonal matrix T and then L transpose. So were you able to find these L and D? Or are you aware how to get this L and D using this L?
No, sir.
Okay, let us discuss that then. So you have your L with you, right? This L is 100, 220, and 333. Okay. So do one thing. Write all the diagonal entries into a new matrix. 100, 020, and 003. Okay. Then what I'm saying is your D is nothing but S square and your L is nothing but L into say S inverse. Will it work good? So we can see that. So A is L dot L transpose. So from here L is equal to cap L into S. So this implies L into S, L into S transpose, which is equal to L S S transpose L transpose. S transpose is nothing but S. So it is L S square L transpose, which is nothing but L D L transpose, right? So this is what you have to recall with you. That if you have your Chomsky factor L, you can find your diagonal matrix D and you can find your new lower triangular matrix L. And from here only you can see this, that your Chomsky factor L is nothing but L into S, where S square is D, so S is D power 1 by 2. What is being asked you to show? Does this make sense? These are the two things you have to remember when doing this type of factorization, that D is equal to S square and your new lower triangular matrix L is nothing but Chomsky factor into S inverse. Can you complete this question now?
Yes, sir.
So shall we proceed to problem sheet 9?
Yes, sir.
Okay. What about question number 1? Okay, first of all, are you aware about this norm, AF norm? Are you aware about this? This F is known as Frobenius norm. It is also mentioned in problem number 2. Yes, Frobenius norm and also Euclidean norm. So have you done question number 1?
Yes, sir.
Is it doable?
Yes, sir.
Okay, so there is just one crux factor in this question. So can you tell me that you must have used one inequality in solving this?
Yes, sir. Shorts inequality.
Yes, but it says if you want to find this summation AIBI square, it is less than equal to
Sigma AI square into sigma BI square.
right. So you have to use this in order to solve question number 1. Okay, sorry for the disturbance. Okay, what about question number 2? Am I audible?
Yes, sir.
Okay. Were you able to solve question number 2?
Yes, sir.
So it is quite trivial, right? Because condition number F on A, which is nothing but norm of AF, norm of A inverse F, it is always greater than equal to norm of identity F, right? And which is nothing but square root n. Right?
Yes, sir.
Okay. What about question number 3?
Sir, please do it.
Done?
No, sir.
So what is the condition number 4 of U with respect to the Frobenius norm? If U is a unitary matrix, what is condition number of U with respect to F? Tell me. Okay, let us frame it like this. If U is a unitary matrix, then what all properties do you have with you? If U is a unitary matrix, then what can you say about U? Some special properties.
U star equal to I.
Yes. So this is the crux of this problem. So if U into U star equal I, so what does this mean? Summation, if I say U is equal to Aij, then what do we have? Summation A ij dot, let me frame it like this, aij square j running from 1 to n is equal to 1 for all 1 less than equal to a less than equal to n, isn't it?
Yes, sir.
So now Frobenius norm of U is nothing but summation I running from 1 to n summation j running from 1 to n aij square and power 1 by 2, which is nothing but summation I running from 1 to n 1 power 1 by 2, which is square root of n, right?
Yes, sir.
But oh sorry, also Frobenius norm of U inverse is nothing but Frobenius norm of U conjugate transpose, right? From star,
Yes, sir.
which is nothing but Frobenius norm of U, because conjugate transpose will not change the Frobenius norm. Which is again equal to square root n. So now tell me what is the condition number of U with respect to F?
And
N. Is this making sense?
So, sigma aij mod square equal to 1, it happens only for unitary matrix.
No, it is not true that it happens only for unitary matrix, but if it is the unitary matrix, then it is true. Okay.
Yes, sir.
The thing is, unitary matrix shares one more extra property. If you will see, the exact property for unitary matrix is summation j running from 1 to n aij dot uh, ajk bar, so bar is the conjugate, right, is equal to delta ik. So this is the thing. This specifically hold for unitary matrix. If this condition is satisfied, then you can say, okay, we have the unitary matrix with us.
And delta ik open like 1 when I equals k and 0 when I is
Yes,
not.
1 if I equal to k, 0 otherwise. Dirac function. Okay.
सर
Yes.
इसका फर्स्ट पार्ट भी बता दें.
Condition 2.
यस सर.
Okay. So are you aware about norm of u2 for any matrix A? Okay, let me make it A. If A is some matrix, then what is L2 norm of A, if you say?
Sir, but in question 3 condition f equals to 1 we have to show.
It is condition 2u is equal to 1 you have to show.
Yes sir, but above you have written n.
Condition 2u means the L2 norm here. It is not the Frobenius norm. It is asking the condition number of u with respect to the Frobenius norm in the second part, right? Or
Okay,
is this
okay. Yes
sheet is
sir, yes.
also changed?
Yes sir, yes sir.
So are you aware about this norm, L2 norm of A?
Yes sir.
So what it is, you can define it in the simplest way as supremum of norm of AX, L2 norm, and norm of X is less than equal to 1. Or it is also equal to this supremum norm of AX2 such that norm of X is equal to 1, L2 norm of X. So these both are same. And it is also equal to the lambda maximum of A star A. Lambda maximum of A star A means the largest eigenvalue of A star into A. So this is the definition. So now if U is a unitary matrix, then norm of U L2 is nothing but lambda max of U star into U, right? Isn't it?
Yes sir.
And U star into U is what? Identity, because U is the unitary matrix. So lambda max of identity matrix. What is the largest eigenvalue of identity matrix?
1.
And similarly for U inverse also, you will get it equal to 1.
Sir, please explain this norm again.
This one,
Yes sir.
it is a definition that if 1 is less than equal to p less than infinity, and A is any n cross n matrix, then LP norm of A is nothing but supremum of LP norm of AX, such that norm of X P is less than equal to 1. So you can also make it equal to 1. This is a definition. And for this, if I say ax is some y1, y2 up to yn, then LP norm of ax is nothing but summation yi power p, I running from 1 to n, whole power 1 by p.
Supremum will not be there.
But
Sir, supremum. Norm 2 equals supremum, but here norm P don't have supremum.
I didn't get you. I am okay. For this, I am saying AXP. For a fixed x, norm of AXP will be this, right? So how come you will use supremum here? Supremum will be here, right? In 1. It is the definition of AX for a fixed vector. If x is fixed for a fixed x, you will get AX to be a fixed number equal to y depending upon x, right?
Yes, sir.
So I am telling you, for say, it is a general thing for any x or say y in Rn. So the what I am saying is, for any y belongs to Rn, y is equal to y1 up to yn. LP norm of y is defined like this. So how come will you use supremum here? It is for fixed number. So for each
Yes, sir.
fixed x where this is true, you have to calculate norm of ax and then take the supremum of everything. But for the it is also true that for especially for 2 norm, the L2 norm, this equation is also true, that you just find the maximum eigenvalue of a star a. I'm not saying it is true for any p, right? For p is equal to 2, this result is also true, because it is quite difficult to find ax for each x, right? You don't know what x you can choose, so it is quite difficult to find norm using this definition. So here we use this definition. Is it clear?
Yes, sir.
Shall we proceed to next question?
Yes, sir.
Okay, so what is it asking? Find the values of alpha and beta for which matrix are singular or diagonally dominant. Can you do that?
Yes,
So
sir.
D part.
So for the D part, you have to work with x transpose ax definition. You want it to be greater than or equal to 0 for all x. So what I mean, start with this alpha 1 0, beta 2 1, 0 1 2, x1 x2 x3, x2 x3, alpha times x1 x2, beta times x1 plus 2x2 plus x3, and x2 plus 2x3, and then alpha x1 square plus x1 x2 plus beta x1 x2 plus 2x2 square plus x2 x3 plus x2 x3 plus 2x3 square. So we want it to be greater than or equal to 0. This implies alpha x1 square plus beta plus 1 x1 x2 plus 2 common x2 square plus x3 square plus x2 x3 is greater than equal to 0, isn't it?
Yes, sir.
So now we have to see what condition should we impose on alpha and beta. So at least one condition you can conclude from here directly, that alpha has to be greater than equal to 0 first of all, right? Because if I take x2 is equal to 0 is equal to x3, then we will have left with alpha x1 squared to be greater than equal to 0. Hence alpha has to be greater than equal to 0. I'm not saying that this will be the condition, but at least this will be the condition with us, right?
Yes, sir.
And along with that, have to do some what else condition shall be imposed here. Okay, let us try to find out the eigenvalues directly. If for the timing, if I find it directly, it is alpha minus lambda and 1 0, beta 2 minus lambda 1 0 1 2 minus lambda. So it is alpha minus lambda. So lambda minus 2 lambda plus 2 lambda square minus 4 minus 1, right? Minus, sorry, it will be minus 1 times 2 times beta minus 2 times lambda. So it is equal to 0. So on solving, it is alpha minus lambda square minus 5 plus 2 times lambda minus beta is equal to 0. So this cubic equation we have, this cubic equation will result in lambda in form of some f1 alpha comma beta, f2 alpha comma beta, and f3 alpha comma beta, right? I'm not very sure how to solve this cubic equation as of now because it will be slightly complicated. Plus alpha times lambda square plus 5 lambda plus 2 lambda, it will be 7 lambda minus 5 alpha plus 2 beta is equal to 0, right? So this is the case. or more or less. But do we want? We want all those lambda I. It has to be greater than equal to 0. So I can tell you the conditional
सर
beta
सर यहाँ पर बीटा इंटू 2 माइनस लेमडा होगा ना ऊपर
ऊपर.
सर आपने
I
-2 माइनस लैम्डा लिया ना, तो वो 2 माइनस लैम्डा.
it will be beta into 2 minus lambda. I'm sorry. So correspondingly our cubic equation will change, right? Okay, as far as my knowledge are concerned, I can't really solve this cubic equation as of now. I'm sorry for that. Because even if alpha and beta are known, then also it is very difficult for me to solve a cubic equation. Okay, for the timing, can we discuss the rest two problems? Those are really theoretical problems. And if time left with us, we can try. I shouldn't say try because I genuinely don't know how to solve this cubic equation as of now. Okay, but just a second. Just a second. It is minus lambda q plus 5 lambda, right? Plus lambda square alpha minus 5 alpha minus 2 beta plus beta lambda, right? So if I make it correct, it is lambda cube minus lambda square alpha minus lambda 5 plus beta plus 5 alpha plus 2 beta is equal to 0, right? So this is the equation, right? Is this equation correct or I'm making any mistake here?
Sir, 2 lambda.
Where 2 lambda?
Sir, not beta lambda, it's 2 lambda, no?
No, it should be beta lambda, right? Beta into 2. This is the case, right? So 1 is common and then you have beta into 2 minus lambda. So 2 beta minus 2 lambda. Okay. So the first equation was right, right? Just a second, what I'm doing here. It is lambda 5 plus beta. Now this makes sense.
Sir,
Yeah.
sir, in the 822 entry, you have written -2 minus lambda. It is 2 minus lambda.
Okay. This is also a mistake by me. I'm sorry again. Okay, let me do it again then. Alpha minus lambda. Then we have alpha minus lambda into 2 minus lambda square, right? Plus beta into lambda minus 2, isn't it?
2 minus lambda whole square minus 1.
Okay. So what I will suggest you is, if I am saying lambda 1, lambda 2, lambda 3 are the roots, then we have certain conditions which you might have done in your, say, junior classes, that any ax cube plus bx square plus cx plus d can be written as x cube minus, say, lambda 1 plus lambda 2 plus lambda 3 times x square plus lambda 1 lambda 2 plus lambda 1 lambda 3 plus lambda 2 lambda 3 times x plus lambda 1 lambda 2 lambda 3 equals 0. So from here you will have three equations, lambda 1 lambda in terms of your eigenvalues, and each lambda will be some function of alpha and beta, isn't it? And then, but do we want these to be greater than equal to 0? So this is a sort of some calculation thing. And I would like to skip it for the time. But this is the way. What I'm telling you, you have to start with this thing. In case it comes in your exam, but it will definitely not come because it is definitely a time-consuming stuff. So, but as far as the topic is concerned, you have to do these lambda 1, lambda 2, lambda 3, find the eigenvalues in terms of alpha and beta, and then say, okay, we want each of the eigenvalues to be non-negative. Okay. Can we proceed to next problem as of now?
Yes, sir.
Yes,
Okay,
sir.
so it is something of this sort, right? The next problem, because ma'am was saying that she have made a change in the sheet. So does your problem is this something of this sort?
Yes, sir.
Okay, so was it doable or you need an explanation for any of the part? It consists of two parts.
Second part, sir.
Okay, first part is done.
Yes,
Yes,
sir.
sir.
Okay, let us come to the second. For the second part, you have to observe that xk is converging to x, right? Can you see this?
Yes, sir.
Yes, sir.
So that is what we have to use in this equation. So if I say this xk is converging to x, then for given epsilon greater than 0, there exists, okay, fix a k, because we have to prove the second inequality for each k, right? So fix a k, okay, k belongs to n. So for each epsilon greater than 0, there exists some natural number n belongs to n such that x of capital K minus x norm is less than epsilon over t power k. Okay, please make it in mind, I'm using capital K here and small k here. Okay, so this small k I am fixed earlier for all capital K greater than equal to capital N. So this is a definition, right, for the convergence. You will see why I'm using this t power k here, but at least if I just write this one, then it makes sense, right? This is the definition of the convergence, that if some sequence is converging in some norm. isn't it?
Yes, sir.
Okay, so let us do this then. Okay, maybe I'm doing something fishy. Okay, we will see. So what do we have? Xk minus small x. So from first inequality we already have this norm tk norm of x0 minus x, isn't it?
Yes, sir.
Right? So you can make it like this: tk x0 minus x power capital K plus norm of x power capital K minus x, right?
Yes, sir.
So which is less than equal to epsilon times norm epsilon plus norm of t k norm of x naught minus xk, isn't it? Does this make sense?
Yes, sir.
Okay, now we have to just play on here. So it is norm of x capital K minus x naught. So you can just write it like this: xk minus x k minus 1 plus norm x k minus 1 minus x k minus 2 plus and so on. The last one will be x1 minus x naught, isn't it?
Yes, sir.
And you know that norm of x, some any, say, let me put I here, xi minus x of I minus 1 is always less than equal to norm t power I minus 1 x1 minus x0, isn't it?
Yes, sir.
So norm of x capital K minus x0 will be less than equal to norm x1 minus x0 plus t times norm x1 minus x0 plus and so on. The last one will be norm t capital K minus 1 norm x1 minus x0. So if I take norm x1 minus x0 common, so it will be 1 plus norm t plus norm t square plus and so on norm t k minus 1, right? So it is less than equal to x1 minus x naught summation I running from say 1 to infinity. If I want to make 0 to infinity, can I write this from here? It was a finite sum, it will always less than equal to an infinite sum, isn't it?
Yes, sir.
And now when r is less than 1, then summation n going from 0 to infinity r to the power n, it is a gp. Sum of the gp is nothing but 1 upon 1 minus r, right? Some of this sort of gp.
Yes, sir.
So just use it here. You will have norm xk minus x0 less than equal to norm x1 minus x0 upon 1 minus norm of t. So r is nothing but norm t. Fine. This is what we need to prove, right? Okay, is it clear?
Yes, sir.
Okay, so the next problem is nothing but Gauss Jacobi and Gauss Seidel. So this is some sort of trivial problem, and you might have done in your undergrad also, right?
Yes, sir.
So can you assume that this problem is quite trivial, the last problem?
Yes, सर एक बार कन्वर्जेंस का बता दीजिए.
Convergence, for the convergence, you have just one condition in order that Gauss Jacobi and Gauss Seidel method converge. You just need to prove that the matrix is diagonally dominant. That's all. Your matrix A is nothing but 2 minus 1 0 0 minus 1 2 minus 1 0 0 minus 1 2 minus 1 0 0 minus 1 2. So you can see that this matrix is diagonally dominant because AII mod AII is always greater than mod Aij, j running from 1 to n, j not equal to I. For all 1 less than equal to I less than equal to n. So this is the condition which have been taught to you in the class also, that if a matrix is diagonally dominant, then Gauss Jacobi and Gauss Seidel method converges. Does this make sense?
Yes, sir. Yes, sir.
Okay. So from my side also, all of the problem sheet has been covered. But in case any of you find any kind of difficulty, or you guys want any kind of extra lecture on a particular topic, you guys can tell me. And it is not a foundation that you have to tell me now only. You guys can think and discuss among yourself. And in case you want any kind of extra lecture, you just ping me on WhatsApp. Any one of you, okay? And rest, I am always available. You guys already have my number, so in case you have a say particular doubt, you can ask directly. Okay.
Thank you, sir.
Okay
Yes,
then.
sir. Thank you, sir.
Okay.
Thank you, sir.